Hi everyone, you're going to have lecture 23 and our topic continues to be transistors. I'd like to remind everyone to please go through what we did in the tutorial yesterday, because we looked at examples of solving circuits that have transistors with a few numbers in them, and especially the way we discussed how to think about the process, trying to get a feel for the circuit, get some insight into whether the transistor in the circuit is active or in saturation, on or off, and the kind of thinking that goes into figuring out whether there is a contradiction with an assumption to make that you make, and so on, and whether you can make approximations. For instance, in a circuit that has a BJT, whether it's justified to neglect the base current or not, depending on the mode of operation it's in, and if beta is a large number, and things like that. So those are very important examples, not just to learn how that specific circuit works, but in terms of how we think about them. So please make sure to revisit those. What I'd like to do today is to more formally discuss something that we have looked at in the context of examples, but I'd like to do it at a more abstract level and a little more formally. And that's this concept of, in general, small signal operation. At least that's a big part of what I'd like to do today. And that eventually also connects to operation under AC mode, when you have a time-varying signal, which is not formally really the topic of this course. This is supposed to be primarily the DC operation of transistors, but nonetheless the connection is a gradual one. So we will talk primarily, or to a large degree, about small signal behavior, and I'll clarify shortly what that means. And I'd like to talk about this first without restricting ourselves to a particular transistor. This could be applicable to BJT, MOSFET, NPN, PNP, N-channel, and P-channel. But consider the fact that all four of these devices are three-terminal devices, right? So you have, for instance, for an NPN BJT, you had something like this: base, collector, and emitter. And all the other transistors that we've looked at also have had three terminals. So for a moment, let's forget that there is this thing right here. Just consider these. And we looked at examples where we had, for instance, a voltage difference here, in this case VBE, and then another voltage difference here that we were interested in, VCE. And for instance, we had examples where you could define an output node right there, like that, and we had grounded this. And we looked at the variations of the output as we varied the input connected to this base node, right? So we had an input between these two terminals, base and emitter, and an output between those two terminals, collector and emitter, the emitter being in common between the two. So to think about it in more general terms, I'll again remove these specifics, and I'll redraw this slightly and put it in a box. Okay, so I want to put it in a box, but I'll redraw it slightly. And I'll draw it like this. I'll say this is my input side, and this is my output side, and this is that common node between them, and I put this in a box. Okay, and in fact, this common node that was there, I'll attach two wires to it, bring it outside, to emphasize the fact that you're really looking at a notion of input and output. And this is a good way to look at, for instance, when you're trying to talk about a voltage gain, right? You have made a small amplifier. On the one hand, you have an input, a small voltage signal that you apply to it, and then you expect a large voltage signal at the output, right? So this is a useful view of things. I'd like to start by asking a question. So imagine I tell you what's inside this box. I tell you there is, for instance, a transistor like this. Okay? And then, of course, maybe you have connected this to some resistor, like the kind of circuits that we had seen, right? Detail. And I say you have a voltage at the input here and a voltage at the output. And I ask you for this, for the voltage gain. And again, I give you everything else also. So there's things that go into building this, some circuit around this. How would you go about finding a voltage gain like that, the voltage gain for that circuit? I want you guys to think about it a little bit. See what are the kind of things that you might find difficulty with, things that you might find represent maybe an obstacle or a doubt on the way to coming up with something like this. And I give you the transistor parameters, and I say it has a beta of 100. What are the things that this depends on? I want you guys to think about that a little. Let me ask the question in another way. If I build two slightly different circuits using the same BJT, but maybe with some slightly different values of resistors and so on, would the gain of the circuit be the same for the two? Would it? It wouldn't. Like in the examples that we've seen, it depends, for instance, on, let's say if you had connected the collector to VCC through some resistor, the value of that resistor would have something very important to say about the ratio of the input and output voltages. But even before you can find this, what is it that you need to understand about the circuit before you can give me numbers? You have to first be able to, with some analysis, establish whether the transistor, for instance, is in saturation or active mode, right? Because if it's in saturation, it behaves in a very different way. The ratio of the collector to the base current is not that large anymore, and all the rest of it. But imagine I narrow things down even further. I say you have a BJT, it's in a circuit, things are built in such a way that the BJT is in active mode, it's not in saturation. Now what? Does the ratio V out over V in become uniquely defined? I even make things more narrowly defined. I say I have given you the resistors and everything that I have connected in the circuit. So you have the full circuit. I have not specified the values of V in and of course V out. But if I have given you a circuit made out of a BJT, whose properties you know, and a few resistors, and they're connected in a familiar form like one of the circuits that we've built so far, can you come up with a well-defined voltage gain defined as such, V out over V in for that circuit? Why not? I have given you everything in the circuit. You have the full circuit. It's complete. Yeah. So you have the complete circuit. I say, I've drawn a circuit for you. Let's just as an example, this kind of familiar circuit. I say, I've drawn this for you. I call this V in and this V out. And I give you the resistors and VCC and the transistor properties. Is the ratio V out over V in something that now I can just come up with a number for this? Some people seem a little bothered by it. Depending on the mode the transistor is in, for instance, this is going to change, right? If I have not specified V in, maybe I've applied a Vin that's so large that it has driven this into saturation, right? Like one of the examples. That's possible, because if I increase Vin, I increase the emitter current, that increases the collector current until this Vout comes down enough that it gets too close to the emitter voltage, and then the transistor enters saturation. So you're saying, well, things would maybe change if I go from active to saturation. But let's imagine I say even more specifically that Vin is within a range which keeps the transistor in the active mode. Now what? Is that ratio well defined or not? Think about the title of our discussion. See if that gives you any clue. Here's another clue. Are transistors linear devices? Well, what is the equation that describes the operation of a BJT? What kind of mathematical form does it have? Exponential, right? How about the FET? It's quadratic, right? It had, in its active mode, which we call saturation for the FET, it's VGS minus VT squared, right? So these are not linear devices. Now, if you're dealing with nonlinear devices, in general, speaking about a constant ratio could become problematic, okay? And that goes to the core of what we are going to discuss now. Well, this circuit that we had, which I just erased, remember when we found Vout as a function of Vin and plotted it, I think sometime last week, looked something like this, right? This was the shape of the curve. And this, again, is not a linear behavior. You can see that, for instance, if I'm here, Vin can be a very negative value without any change in Vout. So I can change Vin without Vout changing. Well, the ratio is changing, right, depending on what the value of Vin is. Now, if I come here, so if I'm here, the ratio of those two things is something. If I'm here, the ratio is something else now. It's this over this. If I come here, the ratio is different again. If I come here, the ratio is different, and so on. So this we saw in an example. So the point is that you cannot talk about a Vout over Vin for the whole range as a single number. You have to specify exactly what you mean. And what you're going to talk about instead is, well, you are going to specify where you are on this graph. For instance, you might have chosen a Vin around this point, so your Vout is here. But then you might choose to vary Vin slightly back and forth around that point. And your Vout would then go from maybe here to here. It would vary between these 2 points. This is the kind of thing that we are going to talk about here. That you are operating around a specific point, and you're looking at how the output varies as you vary the input. And this is a very typical problem that you have in electronics. And that's, for instance, amplifying a small signal that you have picked up from an antenna. The point that you're operating around is called the bias point. And the amount of variation, the variation that you have around it is called the small signal. So consider, for instance, in your lab, you had this function generator, the waveform generator. And you could have a sinusoidal signal with some amplitude. But you could also have an offset, right? You could have, let's say, a sinusoidal signal with an amplitude of 10 millivolts that's added on top of an offset of 1 volt. So your signal is going from 0.99 volts to 101 volts, like that, right? So you have some small variations around a bias point. And that's the language that we are going to talk about or use in this discussion. So in general, we are thinking of, now again, I will, for now, get rid of the specifics here. In a general manner, we are talking about something like this. You are applying a signal here that consists, so let's call this V in. And I'm going to use a notation that's case sensitive. So I'm using small v, but capital for the subscript. And this V in, I will think about this as having two components. A DC component, and that's all capitalized, including its subscript, and an all small signal, all lowercase. Okay? It's just a matter of notation to be able to have things. So your V in is the full input voltage this capital V, capital N is the DC or bias perhaps in the language that we want to use. Part of the voltage. And then this is all lowercase, the small signal part. And similarly, the output that I measure here, if I call it V out like that, I will decompose it as a capital V out like that plus little v out. Okay. By the way, I'm not assuming or proving anything. I'm saying any signal that I have at the input, if it involves small variations around some bias point, around some offset point, I can write it like that. The value of that offset, for instance, it could be its average, plus any small deviation from that. That's all. Now, in AC analysis, we will be explicitly thinking about the fact that this V in, the small signal, is a function of time. It's varying with time. For instance, it's a sinusoidal. Here, we are not really thinking about it in those terms. We are just thinking of V in as a small addition to that bias point. And what is described at the output is that the output is written, again, decomposed into two parts that are added up. One part is the bias point, or the constant component. That's the result of the bias at the input. And then there is the small variation or deviation from that bias point. That's the result of the small signal applied at the input. So I'm not, again, proving anything here. I'm just defining a notation saying this is how we will think about this. Okay? I'm not assuming or proving anything. It's just a language that I'm introducing. Now, if you think about the ratio of V out over V in, so the full V out over the full V in, again, notice I'm case sensitive in the way I write these things. So please follow closely and let me know if I make a mistake. I'll just replace in in terms of the decomposition that I've shown. V out, big V out. No, sorry. You see, I got to be careful here. V out plus the small signal part over big V in plus the small signal part. And this ratio, as we said, as we discussed at the beginning, this is not a fixed ratio. This ratio depends on what the full V in is. If you change the full V in as we schematically described, this ratio changes. So this is, you might say, not a very useful quantity. The goal of small signal analysis is this, is to come up with something like this, a ratio that is the ratio of only the small signal components of the output and input. You see, this is all lowercase. To come up with a ratio like that, which does not depend on Vn. Vn being this thing in the denominator. It's the small signal at the input. In other words, I'd like to have this a gain like this that will tell me the ratio of the small change in the output over the small change in the input, regardless of whether the small change in the input from the bias point, whether that's 1 millivolt or 1.5 millivolts or 1.8 millivolts. This is called your small signal gain. And it's a very useful quantity. And you see it all over the place. And by the way, this is a small signal voltage gain. So it's a voltage over a voltage. You might also define a ratio of an output current to an input voltage. It doesn't have to be a ratio of 2 voltages. Okay? This is called a small signal voltage gain. And it's a very interesting and useful and important concept. One can also come up with, for example, the ratio of the small signal ratio of an output current over an input voltage. Okay. So with this in mind, and with everything that we've discussed now, I have the next question for you. Will this small signal gain depend on anything other than just the circuit parameters? So if I give you the full circuit, I say, these are the resistors, this is how they're connected to the transistor, this is my beta and all that. Will there be a unique value for the small signal gain? Let's do this with an example. This is maybe a good time to put a little more physics into this. This was maybe all a little abstract. Consider this circuit. I apply a voltage at the input. And I measure this output. Now, again, this will be a voltage that you might say includes, so this is a V in like this. So it has two components. It has some bias plus a small deviation from it. So let's say the big V in is 1 volt, the little V in is 5 millivolts. Okay, that's why I've written it like that. And then here you have your VCC, here you have a resistor, and this is my V out. Again, V out has two components. A bias and a small signal. The transistor has a threshold voltage V sub T. So that's the transistor parameters. And it also has a quantity W over L mu C aux that's known. These are just device parameters. Find the small signal gain. That's the problem. Can you think about that for a few minutes? Let's discuss. First of all, just as a reminder, again, we have the complete voltage at the input. That's this V in here. That gives us the complete voltage at the output. But we have decomposed V in into a bias part that gives us a corresponding output, and a small signal part that gives us its own corresponding output, a small signal variation at the output. Now, if I want the small signal gain, well, I just have to find V out for a given V in, and then divide the two. Now, to find V out for a given V in, I need to know the current in the collector, right? This current. Now, this current, maybe you will call it IC, which, sorry, like this, IC. That's meant to be capital C, but maybe that's like G. So I'll just write a bigger C, which is equal to this plus a small component. Now, V out is VCC minus R IC, right? So this, I really have to make sure these two ICs are not confused. So for little c, I will include maybe this. It's even worse. I'll do this for big C. That's not a G, that's big C. Okay. Well, so all I need to know is the collector current. And we have a nice formula for the collector current of the MOSFET, right? What is that formula? Well, to begin with, the formula depends on whether or not you are in triode or saturation, right? And in fact, whether the device is even on. So you see right there immediately that I can't proceed without knowing whether the device is even on or in triode or in saturation. So let's assume that I had used some numbers for all these parameters here, and I did the problem, and I know that the device is in its saturation mode, in the desired mode of operation. Let's assume that we know that. So I'll give you that assumption. Assume that the quantities involved are such that the device is in saturation. Now, for the MOSFET in saturation, this is the output current. The total current, or sorry, I shouldn't call. For the MOSFET, this is the drain, which makes our life easier. So let's call this ID, ID plus ID. Okay. ID. What is the current for the MOSFET? In saturation, half W over L mu C oxide, VGS minus VT squared, right? Now, VGS here is just the full V in minus VT squared. That's the formula. Knowing this, now find the small signal gain. Assuming that the parameters are such that your device is in saturation, so that you have a formula for the output current, well defined, as a function of the input voltage. You see, you have the total output current here. You have the total input voltage here. So what I'm interested in is now to think of this problem as this. This total ID is a sum of the bias part plus the small variations, right? This is the total ID. The total V in is the sum of its bias part plus its small variations. Now I'll finally write V out. Or let's first proceed with finding this little ID, and then we'll put it up there and find V out. So what is the little ID from here? Let me expand things. Now I'll just make a small change here, or reorder things slightly. I haven't changed anything really. It's just a little reordering and lumping. Okay, so now I'll expand. right? I have just done some algebra. Or if you want to completely write this out, okay, I have done nothing but expanding. What should I do next? Or is there something you can observe from right here? Is there a simplification that you can observe? Or a next step that you can suggest? Well, here's a question. What is ID? Capital I sub capital D. It's what? Is the, let's say, the bias component. We don't want necessarily to separate DC and AC, but let's say the bias point, the large part that you're not changing, right? Well, that's the consequence of the large part of the input voltage, right? ID, the big I, big D, comes from this part of the input voltage, right? Big V, big N. So this is it. This is actually, this is big ID. If I put big V in, the bias part of the input voltage, in the transistor equation, I get the bias part of the output. That's that. So those things cancel out from the two sides. So the outcome then is I am left with this. Is there something else I can say? Now here I'd like to ask you guys to make a or an approximation. Suggest an approximation. See if there is something that we could get rid of. You see, I have found a relationship between the small variations at the output due to small variations at the input, Vn. So I've found a relationship between that. Little ID and little Vn. Oh, no, Vn is multiplying it. It's not adding to it. Yeah. Yeah. But that's exactly how you want to think. If Vn is really small, it's a small signal. Yeah, so which term do I eliminate? Do I eliminate the first one? So if I have a very small number, if I take its square, will it? So imagine Vn is a number much smaller than 1. If I take its square, will it grow larger or smaller? Smaller, right? So if you have a small quantity, neglect the quadratic term, right? The second order term. In other words, let's be very explicit here. If I compare these two terms, if I assume that Vn is small enough, if Vn is small enough such that the first term is much bigger than the second term, or such that the second term is much smaller than the first term, then I can say ID is approximately just the first term, right? Now, is that a reasonable approximation? What does that require? It really requires that V in be smaller than the big V in minus VT, right? This is satisfied if your small signal input is much smaller than 2 times V in minus VT, right? Because the rest are in common between those two terms, right? W over L mu C ox. There's a factor of 2, which is not really the big deal. But if the small signal, the small variations you're doing at the input is significantly smaller than the bias amount of the input minus the threshold voltage. So imagine your threshold voltage is 1 volt, and you have put a bias value of 1.5 volt at the input. So you have this quantity is 0.5 volt. If your small variations at the input are much less than 0.5 volt, so if you're talking about a signal of a few millivolts, then this is a very good approximation. Well, there you go. You have found something linear, right? In this case, you can say ID over V in is approximately so this is the small signal voltage to current gain for this circuit. And it's actually called transconductance because it's a conductance, right? It's a current over a voltage, but not current over voltage of the same element. It's some output current divided over some input voltage, hence the word transconductance. This GM is something you will hear a lot about, G sub M. The transconductance of the device ratio, and this is a small signal, of course. But you might not say that explicitly, but now you see it was the nonlinear nature of this device that ended up giving us this V in squared term. And it is because of that that in order to be able to just end up with a linear proportionality and hence get a nice ratio, we had to go to small signals so that we could neglect the second term. Okay? And this is something that you do all the time, right, when you deal with small things. And in the limit of V in going towards 0, the little V in going towards 0, this becomes exact, right? And in fact, you could get the same answer by just using differentiation, right? Look at that formula. Sorry, the one at the top. The full ID as a function of the full V in. If you take the derivative of ID versus V in that first formula, what do you get? You will get W over L mu C ox times V in minus VT, right? So I didn't need to do all this. right? And if you are talking about doing this at a specific point around Vn, around a specific bias point, well, this is going to be your Vn, big Vn. Okay, but maybe as a first step, it's not very insightful to do it like that. So for now, I think it's important to go through this exercise that we did here at least once to see this kind of connection. So I'll remove this from here so as to avoid confusion. But I was just trying to show you that this is what you're doing. You have a signal with small variations. The variations at the output, all we did was this. You're saying if you have some function at the output, well, df is dx times f prime, right? That's all it is. Okay. So this is GM. You will see this kind of thing. The GM for a MOSFET, it has these parameters. And you notice that it does depend on capital V sub capital N. That means it does depend on the bias point. Okay? So when you talk about the transconductance and small signal gain in an amplifier, you have to talk about around which point. Now tell me, if I wanted to have a high transconductance gain, how should I choose my bias point? If I want to increase GM, I have to increase Vn, right? Because it's just Vn minus Vt. So the more I give a larger input bias, the higher the gain, the small signal gain. Of course, there are other worries, right? Because if I have, in this circuit, if I work around a very large input bias, then my output will be pretty low, right? I risk leaving the desired mode of operation. If Vout is too low, I can very easily get into the triode mode. So there are trade-offs. But you can see that as a first step kind of thing, if you want a higher gain, give it a slightly higher Vn. And by the way, you can also think of this as, Vn minus Vt is the square root of the current, the bias current, right? That. Vn minus Vt is the square root of the bias current with some constant of proportionality. So in a MOSFET, the transconductance is proportional to the square root of the bias. This is something that you will see. So I hope this, you will see this and it will be familiar to you in the future. Okay. Now we've found the ratio of ID over Vn, but what about the ratio of Vout over Vn? Well, let's do the same exercise. Remember that the total output voltage this is the total output voltage, is simply VCC minus that R times the total current there. Now again, the total output voltage has the bias part plus the small signal part. And that's on the other side, you have the current, which has the bias part plus the small signal part. Please keep track of whether I'm using capital letters correctly, and if not, let me know. Now I'll just rewrite this. Can I make an observation here? VCC minus RID, this is just your capital V capital out. By definition, that's your bias point. So from here then, look how nice that is. Your small signal output voltage is just minus R times small signal output current, which we have from before, because that's just this was my GM, right? So I can say ID is GM times Vn. And GM is what we had above. You see, these are all small signal variables. Except for this bias point, which is all capital. I've just copied what we had up here. There's nothing needed. Let's take a short break. I want to do a quick graphical representation of what we talked about here. Think about the fact that here we calculated this transconductance, this GM, for that MOSFET, right? And the circuit was very basic. There is really just a MOSFET there and a resistor there. This transconductance didn't depend on that resistor. It's just as long as we are in the saturation mode for the MOSFET. Okay? Well, remember the formula for the current. ID, this is the total current, small I, capital D, as a function of the total input, small v, capital N. Right? As long as your device was in saturation, the formula was just that quadratic equation that we had here, up here. There in the middle. ID, a square function of Vn minus Vt, right? So if I were to plot that, I'd get something like this, right? A second order plot. All we are saying graphically becomes this. If I have, let's say, given it, now consider this. If I say my V in is this, okay? Which then gives me this value of current. Now let's call this capital V capital N, my bias point. Okay. All we did was to add some small variations around this. That then corresponded to these variations around ID. Okay? So for instance, if this point, if you say this difference is little v in, this difference here is little ID. That's the small signal thing, right? So you've moved by a small amount on the horizontal axis, and correspondingly, you've moved by some amount on the vertical axis. And in the small signal limit, these variations at the input, be it now an increase in, with respect to your bias point or a decrease, if they are very small, you're essentially saying you approximate that curve with a line, right? That's what we did. And that's why you can find a constant ratio. This is graphically what happened. The ratio of that ID to this V in is just the slope of that curve. And you can see that, of course, the slope depends on around which point on the curve I'm operating. If my V in was smaller here, I'd have a smaller slope. If my V in was larger, I'd have a larger slope. The question here is this. What if my bias point is at V in equal VT, right, where I have not quite turned on the device yet, right at this point VT? At that point, if you add a small signal to it, you will have this small slope there, right? Now, what is the slope at that very point? It's V in minus VT, but if your bias point is VT, the slope at that very point is 0, right? So if you give it a very small signal at that point, you will not get a significant gain. To first order, you'll get 0 gain, right? You will have to deviate from that a little bit to get a non-zero GM. In other words, your GM here at this point is 0, right? And you see that from the formula. This is just a graphical description of the same problem. Notice how the ratio ID over V in, which is GM, let's write that GM, which is the small signal ratio of these, your transconductance, depends on the bias. Where you are on that curve, because the slope would be different. You can do the same thing for the BJT. The difference is for the BJT, if you're talking about the collector current versus the base input voltage and input at the base, if you are in its active mode, the formula is not a quadratic equation, it's an exponential equation, right? So I will not go through all the details of that, but for the BJT, if I build a circuit like that, and I have this, assuming we are biased in the active mode, and again, remember, what we call active here is what we call saturation for the MOSFET. If you call this the collector current, your GM would be the ratio of small signal collector current over small signal input voltage. And that's essentially approximately, and in the limit, it's, like I said, it's this, right? So I don't want to, again, write the input and output as an expansion, as a sum of bias plus small signal, because it's very much all the same exercise. all the same exercise, except that the formula, the current is, recall for the BJT, is an exponential function. Sorry, this is the differential for the of the full current. Let's write the full current. The full collector current is some saturation current e to the V base emitter, which is V in over. Now this VT is different, by the way. Again, opportunity to get confused, but this is the notation in the literature. Thermal voltage here, right? The other one is the threshold voltage of the MOSFET. Threshold and thermal both start with T. What can we do? So if you take the derivative here, you will see that it's pretty straightforward. But anyway, so if you do repeat the same exercise like we did for the MOSFET, and show that GM will be, what will it be? Imagine you're trying to do that exercise very quickly in your mind. All the same thing that we did for the MOSFET over here. What would the outcome be? IC over, very close. That bias current over VT. Do this at home. Go through those steps. This is, again, an exercise that will reinforce this concept. All you're doing, the same thing, except that instead of the second order equation, you have an exponential. I did it in a shortcut way, because I said that the small signal gain is just dIC over dVin, Vin, which is this. And the graphical representation is again the same, except that your curve, instead of being quadratic, is exponential. If I draw it, it will look the same anyway. But you would expect, which one would you expect for, you know, now it's apples to oranges because the two devices are different. But if you were to somehow, you know, a very rough rule of thumb kind of thing, say which one has a higher transconductance, would you say it should be the BJT or the MOSFET? In a very loose kind of way. Again, it's apples to oranges. Of course, we are not saying every BJT compared to every MOSFET, but for somewhat of a comparable sets of parameters. The BJT, why? Because it's exponential compared to this, right? And in fact, look at the GM for the MOSFET. GM for the MOSFET, this is GM. It's proportional to Vin minus Vt, which is the square root of the bias current. You see? Vin minus Vt is the square root of the bias current. Whereas for the BJT, it's the bias current itself. So you might see a MOSFET that's biased in a circuit, you know, such that transconductance is maybe 1 milliamp over volt, whereas for the BJT maybe it's 10 milliamp over volt. Okay. And similarly, you can have a small signal voltage gain, which will be just the transconductance times R with a minus sign. The circuit is similar because, and the minus sign comes from the fact that if you increase the input, the output decreases, like we've seen in some of the examples. What the transconductance tells you is how much gain you can get out of the circuit. How good an amplifier you can make, right? And in fact, here's something fun. You see, if I want a high transconductance to get a high gain, see again, look at this. The voltage gain was just that resistance times transconductance with a minus sign. If I want a high transconductance, I need a high bias current, right? Well, if I bias my circuit around a high current, it means, so I'm keeping it there. Even if I'm not applying a small signal to it, I have kept it at some high current. Well, I'm consuming quite a bit of power, even when I'm not feeding it a small signal to amplify. So you want higher gain, you need to consume more static power. So also then show this also, that V out, little v out over little v in, so the small signal voltage gain will be minus Gm times R. This is exactly like in the previous circuit. And of course, you have similar things with the p-channel MOSFET and the PNP BJT. So connecting to that question that you just asked, how much gain you get is really a function of where you bias things, because you see that it clearly depends on the bias current. And so I'd like to spend a few minutes talking about biasing now. We've actually, in fact, done this already. We've done some numerical examples of circuits where we've looked at DC behavior. That's biasing, basically. You're saying, I want my transistor, my DC voltages and currents to be such and such values. Here's one common way of biasing a transistor circuit. Let's say if you wanted to make an amplifier like this, and you wanted to bias it around some current. You wanted to give it a fixed input voltage. Well, here's one way. And these are not necessarily equal, right? So this could be an emitter resistor, a collector one. Here, call this R1 and R2. And we talked about an example like this. This would bias it around a certain point. And then if you introduce small variations, say if this is your VCC, if you bias it around a certain point and then introduce small variations, so if here you have some bias value plus some small signal, then basically neglect the small signal first, find the bias value, you'll find the current and so on, and then add a small variation, the kind of thing that we just did. Then you will find an output that is some bias point plus some small signal variation. Now, this is an example of biasing. You won't very commonly see the small signal also applied to the same point there. I just did it. This is okay, but this is not what you will see very commonly. But this way of biasing is common. Here's another way to bias a transistor. So let's say if you wanted the same type of amplifier, this is another way. We'll give you, you solve this in DC. It's all DC. It's like, I think we did an example very similar to this, if not identical. This is another way of biasing it. And you could do this with a MOSFET also. Here's another example. Let's do with a P-channel MOSFET. And you could have something like this. Again, not very dissimilar to an example we did yesterday, I think. There's other ways of biasing. For instance, a current mirror that we saw, I think, last week. Well, that was a type of biasing. Here, I'll draw a current mirror with a PNP transistor. Let's say this is minus VCC, and this is ground. This was a current mirror. We did it last week, I think, with the MPN. This is one with PMP. I think you had also an exercise on it in the homework. Basically, the left-hand side acted as a diode. You have short-circuited the base and collector, and it's this VCC minus that 0.7 volt drop that you have. That's left for this resistor. That determines the current. The current in the right-hand transistor is just the mirror of the current of the left-hand transistor, or the same current. The current has been mirrored, as long as the two transistors are identical. And so by changing the value of this resistance, you change the bias point, the current at which you're operating. There are multiple different types of biasing. So these are just some examples. But you might be wondering, really, normally, how would you add your small signal to a biased circuit? I said this is not applying the full signal at the top here is not very common. In fact, often this is connected to the same VCC that you have. That's not your input. So how do you feed a small signal to this? How do we feed a small signal? And again, the scenario that you're typically dealing with is that your small signal is some AC signal. And this is where things start kind of going beyond the calendar description of this course. And that's somewhat maybe strange and unfortunate, but this is what time allows. So I'll have to give you a little bit of just qualitative description. We haven't been talking too much about capacitors for a while, so it's a good time to do so. Consider this capacitor. And let's say it has, I have applied some, so this is connected to some other stuff, some other circuit, and some other things are connected to it here. If things are in DC operation, if you have a circuit in DC and it has a capacitor, what is the current going through? DC steady state. 0, right? In DC steady state, this is like an open circuit. It's something we've been dealing with for a while. So basically, it's as if it doesn't exist. If you have a voltage V1 here and a voltage V2 here, in DC, there is no direct connection between them. That's an open circuit. Here is something else that we have seen kind of, to some degree quantitatively, but not maybe fully. We've seen that a capacitor does not like sudden changes in its voltage, right? Well, we've actually seen this quantitatively, right? A capacitor does not like sudden changes in its voltage. Imagine I have a circuit with a bunch of things there and this capacitor there. And then I take node 1, the voltage V1, I instantly increase a little bit. So I add a small pulse, right, in no time. What will happen at node 2? What's that? It will do the same thing because the capacitor does not like a sudden change of voltage between its two ends. So if I pull one end up, the other end will have to go up momentarily if I do this very quickly, right? If I do it instantly, the other end will have to go up instantly too, because otherwise requires an infinite current through the capacitor. We've seen this before. This is, for instance, what we saw in a clamping circuit, but in other examples too. Okay, so I just said that if I had a signal that was DC, no change in time, there would be no connection between V1 and V2. On the other hand, if I had a signal applied to V1 that changed in no time, so changed instantly, then V2 would have to change instantly also. The capacitor would do that. So it's as if for a time invariant signal, for a DC signal, the capacitor is an open circuit. But for an extremely rapidly changing signal, the capacitor is a short circuit, because if you change this side, the other side will also follow momentarily. Now, if you change things not instantly, but relatively rapidly, so you're neither in DC nor changing things instantly, but you're changing things with some frequency. Let's say in your cell phone, you have things working at a few gigahertz, right? So your signals are changing on the time scale of a nanosecond. It's not instant, but it's pretty rapid. The capacitor in this circuit would allow most of that signal from the left to be sent to the right. It would act not as a perfect short circuit for that signal, for that frequency, but as a significantly connected piece. In fact, it would have some equivalent of a resistance for that frequency that you call impedance. And this is really, again, the subject of AC analysis. But the outcome of this discussion is this, that you can use a capacitor to couple a high frequency small signal to an otherwise DC circuit. Let's be more explicit. If I go to one of these amplifiers that I drew before, I can bias it like this. And then apply my small signal V in, which if it's a high frequency AC, well, if it's an AC signal, apply it there. The DC bias point of the circuit is determined by just these resistors. The capacitor is open in DC. On the other hand, if this V-in has relatively rapid variations, those variations will be transferred to the right-hand side of this capacitor. So effectively, at this node, we see a DC or bias voltage that's determined by the DC behavior of the circuit. But if V in is a small signal that varies in time, if it's AC, a good chunk of it will appear at node 1, just added to the bias point. Now, the higher the capacitance, the lower the frequencies that it will let through. And to appreciate that, we don't have time today, but we can gain a little bit of insight by going back to our RC circuits. Remember, if you want a capacitive circuit to respond fast, do you want a high time constant or a low time constant? Low time constant, right? Now, so I want a small RC, right? So do I want a large capacitance or a small capacitance? Think about that. For this to really make sense, if I could ask you guys to review a most basic RC circuit before next time, okay? Just an R and a C in series, and have an input and output, okay? Go review that. It's a useful exercise anyway, right? Just review this circuit. Review both of these, R, C, and input, and this. And this is your output. This is something you've done many times. Just go review it briefly. But anyway, this is not really, I mean, like I said, AC analysis is not part of our discussion. But we want to just maybe to some degree just agree or take this from me that this is where AC analysis of transistor circuits starts. And you use this kind of coupling capacitances to feed your AC signals in. And in fact, the answer is for this kind of coupling, you want a large capacitance. But anyway, we'll talk briefly about it a little more next time. Thank you.